So I want to prove, we're going to prove the distributive property of the dot product, and I'm going to prove it in 2 space. The proof in 3 space is very similar, but because we're doing these proofs by breaking things up into the component level, we kind of need to know how many components we have. Okay. You will be asked to prove some of the other properties in the homework. Just want to give you a reminder that anytime there's a proof, whether it's an even numbered or an odd numbered problem, solutions to those proofs are posted on Canvas so that you can check your work. And when you're writing a proof, it's not necessarily going to match mine exactly, because it's kind of like writing an essay. And so if it matches exactly, you get a little bit suspicious. Now, there's not a whole lot of creativity in proving these properties, so I'm not going to be suspicious if somebody writes a proof that matches mine exactly, but it could be correct if you phrased things a little bit differently. But if yours differs too much from mine and you're not sure whether it's correct, just give me a call. Come visit me in office hours, shoot me an email. Happy to take a look at the work that you've done and give you feedback on it. Okay, so if I'm looking at the distributive property, I'm going to need 3 vectors in 2 space. Okay, so first thing I do in a proof always is introduce my objects. So I'm going to let A be A1, A2. That's a vector in V2. I'm going to let B be B1, B2. That's also in V2. And I'm going to let C be C1, C2. That's also in V2. Okay, so I've identified my objects. I've given names to my vectors. I've named their individual components, and you'll notice there are no bars over the components because the components are numbers. These are the vectors. And I've said that we're working in 2 space. That tells me that these components represent real numbers because that's the definition of V2. It's 2-dimensional space working with real numbers as the components. Okay, now my claim is that A dotted with B plus C is A dotted with B plus A dotted with C. Okay. Now, he's very careful to identify that that's the claim. I find it helpful to have written down the thing I'm trying to prove. But I don't want it to look like I'm stating that it's true at this point, because if I already knew it was true, there'd be nothing to prove. Okay. Now, I'm just going to label that this is the left-hand side, and this is the right-hand side. And remember, the cardinal rule in writing proofs is that when you're proving an equation, you can only work with one side of the equation at a time. So I'm going to pick a side and start with that. And I have 2 options. I can, let's say I start with the left-hand side. I could simplify it until I arrive at the right-hand side. That's one option. The other option is I could simplify the left-hand side. Then I could switch, simplify the right-hand side. If I can simplify them to the same thing, then I can point out that they're the same. That's what I call the 3-paragraph method. So paragraph 1, simplify the left side. Paragraph 2, simplify the right side. Paragraph 3, say, oh look, they're the same. So I referred to this the last time we did a proof, but the last time we did a proof we just started on one side and arrived at the other. So I think this time I'll use that 3-paragraph method. Okay. So I'm going to, let's see, I'll just work over here. So I'm going to say the left-hand side is A dotted with B plus C. I'm going to be, by the way, proving this in painstaking detail. Okay, so that's about the only equal sign I don't need to identify because that's just that I've labeled that that's the left-hand side. Okay. Now I'm going to say that that's equal to A1, A2 dotted with B1, B2 plus C1, C2. If I'm doing painstaking detail, I need to provide a reason for each step. This reason, once again, is basically because we said so. Notice that means it's very important that we actually did say so, that we did actually define these vectors. And so this is just the definition of vectors A, B, and C. Okay. All right. Order of operations, I would do what's in parentheses first. Okay. So this is going to be A1, A2, dotted with B1 plus C1, comma, B2 plus C2. Now that is just the definition of vector addition. Now I'm ready to work out the dot product. So that's going to be A1 times B1 plus C1 plus A2 times B2 plus C2. So it's the product of the first components, this number times that number, plus the product of the second components, this number times that number. That is just the definition of the dot product. And I think I'm going to take this one step further. Let's see. The whiteboard's a little bit small, which is unfortunate. Okay, I'm going to just come up here and continue over here. I'm going to just, at this point I'm just working with real numbers. I'm going to use the distributive property of real numbers. So I'm going to say that's A1B1 plus A1C1 plus A2B2 plus A2C2, and that's just the distributive property of real numbers. So at this point, I have simplified the left-hand side. Now, if I wanted to keep going, I could and try to arrive at the right-hand side. I said I wanted to do this using what I call the three-paragraph method. So I can say, okay, that's what the left side simplified to. Let's switch gears now and let's talk about the right-hand side. And you'll notice there's no equal sign connecting this to the left-hand side. This is, if I were writing an essay, I would be indenting because this is a new paragraph. Now I'm talking about something different. So the right-hand side was A dotted with B plus A dotted with C. That was from the original equation that got erased a little while ago. The drawbacks of having a small whiteboard. Okay, so again, that's just, I labeled that as the right-hand side. Every other equal sign is going to need justification. So I'm going to say that's A1, A2 dotted with B1, B2 plus A1, A2 dotted with C1, C2. And that is just my definition of A, B, and C. And now I can do the dot product. This is going to be A1, B1 plus A2, B2. And this is going to be plus A1, C1 plus A2, C2. Now, really, these are in groups. That's the dot, that's this dot product, that's this dot product. Now, if I compare this to what I have, it looks like I've got the same terms, but they're grouped a little bit differently. Now, these are just real numbers, so I know that the grouping isn't important here. I can basically use a combination of the associative and the commutative laws to change the grouping and the order in which things are. And that's the one time when you're using a combination of the associative and the commutative properties for real numbers to just rearrange and regroup the terms, that you can do two things in once. Because it's kind of tedious to say I can drop the parentheses and I can change the parentheses and then I can switch the order. So I'm going to just say this is the same as, I basically, to get a perfect match with what I have up here, I want to switch the order of those pieces. So I'm going to say that's A1B1 plus A1C1 plus A2B2 plus A2C2, and that's the commutative and associative properties of real number addition. Okay, so now the right-hand side looks like the left-hand side. So I'm done with paragraph 2. There is a third paragraph. The third paragraph is that the left-hand side equals the right-hand side. You do want to state that. In this case, it's pretty clear that the reason I stopped here is because I had the same thing as what I had here. But sometimes as proofs get a little bit longer, you might have forgotten where you left off previously. And so if you stop and somebody's reading your proof, they might be, did she get bored? Was she really tired? Or was she done? This says I stopped because I'm done. I did what I said I was going to do. I proved that the left side was equal to the right-hand side.